challenge here. Here's a very simple record type, the kind of thing we probably see all day long. Email address and email verified, which is set if you own the email address. So how many things are wrong with this design? Now, if you program in C# or something, this is probably what your typical code looks like. It's very simple. There's strings everywhere. And I suggest there's actually quite a lot wrong with this design. In fact, I think there's four things that leap out at me. So the first thing is which values are optional. So some of the values are optional and some of them aren't. Like the middle initial is probably optional, but the first name and the last name is probably not optional at all. But that's not indicated by this code. So what else? What are the constraints on this code? So, for example, the first name, can it really have 1 million characters in the string or 64K characters in the string? Can it be blank? Can it contain line feeds and tabs and stuff? I mean, there's probably some constraints about what can go into that string. That is not visible from this definition either. So in this particular case, the first name is not allowed to be more than 50 characters because I'm going to be putting it in a database. Which fields are linked? So in this case, if I'm doing a multi-user system and one person updates the first name and someone else updates the last name, I should get a concurrency error. That shouldn't be allowed. But if one person updates the first name and someone else updates the email address, that might be perfectly legal. So there might be, the atomic units of transactional updates may be different from what I've got here. And that's not indicated here either. So, for example, the name part has to be updated atomically, and the email address has to be updated atomically. And finally, what is the domain logic? So we have this is email verified flag. This is a very common thing you'd see in C# code. But it's not very clear whether I should set it or not, and what rules should I set it? Under what circumstances should I set it? Can I just set it to true or false, regardless? There must be some business logic around it, but it's not clear at all what the business logic is here. Somewhere in the code, the business logic exists, but it's not here in the type itself. So it would be great if you could actually encode that logic in the type. So in this particular case, the business logic is you have to reset the verify flag. If you change the email, you need to re-verify the email before you can continue. So which values are optional? What are the constraints? Which fields are linked? And what's the domain logic? F# can help with all of these questions, and in fact, Haskell can help, and Camel can help, and so on. But I'm picking on F# tonight because it's an F# group. So, domain-driven design with the F# type system. My name's Scott Wlaschin. I managed to grab the Twitter handle Scott Wlaschin, luckily. I have a blog, f#funandprofit.com. That's me. And I've just started a consulting company, fpbridge.co.uk. The slides for this talk are available at f#funandprofit.com/ddd. So, domain-driven design, for those who are unfamiliar with it, is about designing really user-centric design, domain-centric design, not designing from the database, or designing code because it's easy. It's easy to create classes, so I'm going to do a class, an object-oriented design, or a database-driven design. I'm going to design it based on what the actual business domain actually represents. So focus on the domain and the domain logic rather than the technology. I'm not actually going to go too much into the book stuff. I'll talk a little bit about it, but I really just want to talk about what it would mean to write code based on what the domain rules are and the business rules are. So, functional programming, domain modeling, this talk is the intersection of the two. Not often, as far as I know, do you actually have talks about the intersection. You have a lot of talks about functional programming and monads and all this stuff. Not a lot of talks about how you can do very cool domain modeling. And I think actually it's a huge advantage over standard languages like C# and Java and Python even. Okay, so I'm going to demystify functional programming for people who need to have functional programming demystified. And the rest of you can just close your ears. I'm going to talk about functional programming for real-world applications, again, to emphasize that it's not just for mathematical things or financial things. F-sharp versus C-sharp for domain-driven design. And then understanding the F-sharp type system, which is algebraic types. And basically, I'll be explaining algebraic types for people who are not familiar with them. And then finally, now that we understand algebraic types, I'm going to actually talk about how you actually design with them. So, let's start with demystifying functional programming. This is just a little fun thing I put in here because a lot of people seem to be very scared by it. And, people think functional programming is scary because of all these buzzwords like functor and catamorphism and applicative and monoid and monad, the most evil word of all. So Paul Homer here has a really hard time with all these words, and he thinks his head's going to explode. And I think that it's really not that these words are scary, it's they're just unfamiliar, right? And if the problem is they come from mathematical terminology, because the maths people got there first. And if the non-math people had got there first, we wouldn't be calling them functors, we'd be calling them mappables. And instead of a catamorphism, we'll have something like a collapsible, an aggregatable, or a chainable. Okay, so they don't sound so scary if they had different names. Now, you still might not want to understand what they are. Like Homer here, it's like, I don't know what a mappable means. I don't know what a chainable means, but it doesn't sound as scary as a monad somehow, So if you're talking to people, this is maybe one thing, just call them different names and they're not quite so scary. I'll tell you what really is scary. Object-oriented programming. And I'll prove it to you. Because you have really scary words like polymorphism and inheritance and interface and generics and covariance and solid. And solid itself is five different things, SRP, OCP, and each of those things is other things. And then you've got IOC and DI and ABC and MVC and all these buzzwords, okay? So you have to remember thousands of little buzzwords to do object-oriented programming. And that's why I think object-oriented programming is scary. Now, if you didn't know object-oriented programming, you'd think it was really scary. It's just that you happen to have grown up with it, and therefore these things don't seem scary to you. But they are scary to someone who's a beginner. And I actually think that functional programming is easier because there's actually less concepts. There's only a couple of core, pretty much all the concepts on the previous page. That's all you need to know. So there's actually less concepts in functional programming than in OO programming. So just going back to this slide for a second. I think you're actually not going to need much of this stuff. And certainly in this talk, you're not going to need any of it. So don't even think about it. It's not going to be a scary talk. I'm going to talk about types, not functors or monoids or monads or anything. So, functional programming for real-world applications. So a lot of people have heard that functional programming is really good for mathematical, scientific tasks, really good for complicated algorithms, good for parallel processing, but you need a PhD in computer science to understand it. Well, the first three things are actually true. It is really good for all those things. And it's so not true that you need a PhD. I think there's a lot of mysterious stuff around functional programming. I think once it becomes more mainstream, people say, oh, it's obvious. Why did we ever think it was hard, So I'll tell you what I think functional programming is really good for. It's really good for boring line of business applications, okay? I call these blobbers. So, how many people here do blobber development? Most people, yes. So, unless you're doing, some people do scientific stuff, but most of us, I think, that's how we make our daily living is doing blobber development, okay? So, let's talk about blobber development. There's a couple of things you have to have for blobber development. First thing is you need to express requirements clearly because you're trying to communicate with the customers. The second thing is you need to have a rapid development cycle because the customers keep changing their mind and you need to deliver something before they change their mind again. You need high-quality deliverables because there's nothing worse than going back and fixing a bug that you made 6 months ago, and that's really terrible. And meanwhile, the customer wants you to work on something else. So these are all really common requirements for blobber development. And it's interesting that the whole agile movement and XP came out of blobber development at Chrysler. Express requirements clearly, that's customer on site, and then the rapid development cycle is continuous integration and continuous deployment, and high quality deliverables is unit testing and TDD and BDD, and blobber development is very correlated with this stuff. Now F# is also good for blobber development because it's really good for expressing requirements, and that's what I'm going to talk about today. There's a REPL, of course, so you get this nice rapid development cycle, which is great, and you can avoid a lot of boilerplate as well because of the way functional programming works. And high-quality deliverables. Not only can you do your standard unit tests and BDD stuff in F#, but the type system itself ensures correctness in many, many ways, and I'll be talking about that today as well. Very important thing, if you're going to be working on boring stuff all day long, you should be having some fun as well. So I put fun as the fourth requirement for Blobber development. Okay, and F# is a fun language. I mean, I don't think anyone really claims that C# or Java are like fun languages. You know, they're competent, they're useful, but they're not fun. F# is a lot of fun. Luckily, fun is a keyword in F#. So how good is that? And I think I stole that one from Phil. So, okay, so F# hearts Blobber development. Very good. So let's compare F# and C# for domain-driven design, and we're going to take a very simple, immutable object. Now, in domain-driven design, there's this concept of value objects versus entity objects, and value objects are immutable and they don't have identity and so on and so forth, and entities have identity and so on. So we'll have a quick look at how F# and C# compare with those. So for value objects, equality is based on comparing all the properties in the object. So, for example, if you have two personal names, if the first name and the last name are the same, it's the same thing. Even if they're different objects with different pointers, different references, they're the same object, they have the same value. So strings are a good example, and integers are a good example, and a personal name should also be that. And automatically it has to be immutable, because if you change it, it's a different object. So how would you do this in C#? Well, here's a typical C# class, personal name, it's got a constructor, it's got a couple of public properties. I'm doing private sets, because it's immutable. Good best practice there. And that seems pretty good, except I've forgotten something quite important, which is equality. So classes are reference types. So just because I've defined this, two classes with the same values are going to compare differently because they're reference types by default. So I have to override equality as well. So here's the extra code that I need to write for equality, and you guys have probably written this millions and millions and millions of times. You have to override get hash code, you have to override equality, and you have to add equals again. How many people have made a mistake in overriding get hash code at some point? Like with a mutable object and the hash code didn't change, and in the dictionary, yeah. Very annoying. So, so there's the C# code. Let's look at the F# code. So here's the F# code to define the type. That's a one-liner. But you say, well, you know what, I've forgotten to do something really important. I've forgotten the equality code. So let's write the equality code for that too. There you go. That's the equality code. So in F# you don't have to write the equality code because types that you declare are automatically value objects. They automatically have equality based on all the properties. That's the default behavior in F#, unlike C#. And of course, the best code is no code at all. So if you don't have to write get hash code and stuff, you can't possibly have a bug in it because you haven't even written it. So there's one line of F# versus 30 lines of C#. Okay, what about entity objects that have identity? So there's some sort of ID. In this case, two people are the same if they have the same ID, but you can change the name, like this person had a sex change. They went from being Alice to Bilbo. So immutable content, generally, although you don't have to have immutable content. So how do we do this in C#? Same thing, we write a class. This time I've got I removed the private set so the name is mutable. And I have to override equality again in a different way, subtly different way from the first time. Okay, I have to compare an ID. Okay, let's look at the F# equivalent. So in F#, you tag it with custom equality if you want to override equality. I'm not sure if that's really required, but I like to do it because it tells me that I'm doing it. Then you have to override the get hash code. And you have to override equality. The nice thing is the overriding quality is actually a lot easier because if it's a person, you compare the IDs. You don't have to do a null test because the type can't be null. So that eliminates a whole class of issues right there. No null checking. Now, I actually don't like using customer quality because this person type, sometimes you might want to compare it by ID, but sometimes you might want to compare it by reference checking if it's in a cache or something, especially if it's a mutable object. Sometimes you might want to say they're equal if they have the same name. So equality is not always obvious. So when I have complex types like this, I actually like to use the no equality attribute, which I think is actually a fantastic addition to F#. And what that does is it means you literally cannot compare these types. So if I have two persons, I can't compare them. I can compare their IDs, I can compare their names, I can dot into them and compare different properties, but I can't write person 1 equals person 2. I think that's a really fantastic feature. So, one of the nice things about the F# type, again, is it's immutable. So here we have our immutable person. And one of the really nice things about immutability, along with many other things, is that let's say you have some sort of constructor that you pass in a name and you create a person. If the name is valid, you're going to create something, and if the name is not valid, you're going to return an error or you're going to return a none option. What's so great is there's ways to hide the built-in type constructor, so you can expose the type but not the constructor, so that you actually have to force all the code to go through this constructor here. And because it's immutable, any time you want to change anything on that object, you have to make it go through this constructor, which is fantastic because all changes to anything have to go through this one constructor, which means that all the validation logic, all the invariants are in one place. Now, the amount of trouble that people have with trying to maintain invariants when you have mutable data structures is just awful. So, immutability just means if you have to create a new one, you recheck all the invariants every single time, and it's much, much simpler to do. So that's a little plug for immutability there. So let's look at the C# code that we have so far. Here's our personal name and our person, and the person used as a personal name. So, a couple of questions. Do you think this is a reasonable amount of code to write for these simple objects? And I think, how many lines of code is that? 20, 30 lines, maybe 60 lines altogether, I don't know. I think that's too much code, personally. Secondly, do you think a non-programmer could understand that code? If I went to the product owner or the on-site customer and I said, oh yeah, we've got this personal name thing, and can you just review it to make sure it's working, it's the right code? It's like, they couldn't possibly review it, I don't think. And finally, there's a subtle difference between these two classes. One of them is structural equality, comparing all the properties, and the other one is an entity type where you compare on the ID. Is it obvious from this code which one is which? No. It's buried in the equals method. That's the only way you can tell how equality works. And that's really quite a really important attribute of an object, is how equality works, but it's buried inside the code here. Now, there are ways of doing that. You can tag things with an I value or an I entity. If you look at the domain-driven design examples in Java and in C#, people do that all the time. They tag stuff with a value object and an I entity. It's one of these marker interfaces, which I always think a bit of a code smell. So if you're using marker interfaces like that, that tells me there's something a bit fishy, really. All right, let's compare that with the F# code. So here's the two types in F#. 6 lines of code, 8 lines of code if you include the attributes. So, same two questions. Do you think this is a reasonable amount of code to write for a simple object? And I think yes. You couldn't get much simpler. I mean, really, this is about as little code as you could write to get away with what you're trying to get across. Secondly, do you think a non-programmer could understand this? If I went to somebody and I say, what's the definition of a personal name? And they say, well, it has a first and a last name, okay? I could actually show them this code, and they could say, yes, that's right. Even without understanding F#, without being a programmer at all, they could look at that and say, yeah, that looks right. So I think that's really fantastic. And finally, can you tell the difference between the ones with structural equality and no equality or ID equality? And yes, you can, because it's right there in the attribute. So just to summarize C# versus F#. Value objects are non-trivial in C#, they're trivial in F#. Entity objects are non-trivial in C#, trivial in F#. Value objects by default is true in F#, and if you're doing domain-driven design, you should be using value objects by default, unless there's some reason to have an entity. People way overuse entities in domain-driven design. Can you tell value objects from entities at a glance? Yes, you can in F#. And is it understandable by a non-programmer? So in all this whole list here, F# does better than C#. So, and this has got nothing to do with, so I'm talking purely about design stuff here. I'm not even talking about functional programming here. This is purely a design thing. Now, that last thing, understandable by a non-programmer, is a really important thing for domain-driven design, because domain-driven design is all about talking to the customer and having the customer and the programmers on the same page, on the same wavelength, and not having a separation between them. And it's the idea it's a collaboration between the two. So that's what I'm going to talk about next. F# for domain-driven design is all about communication. And the idea is if you can communicate and you share the concepts of the domain, then the code will actually be much more accurate. There's actually a good example of this. Dan North, is it? Was learning. He joined this company where they were training traders, and he actually went on the trading course along with their normal traders. And that was the thing. They taught all the developers how to trade, so that the developers actually understood trading at a deep level, and they taught the traders how to program. And the idea is that at that point, the code could be turned around in weeks. You know, and both sides knew exactly what they're talking about because they'd both been trained to talk about the same stuff in the same way. Okay, so communication is hard. What does this word mean? Unionize. Okay, well, if you're an activist, if you're into social justice, it means unionize. On the hand, if you're a chemist, it means unionize. So there's an example of a word with two different meanings depending on the context. And domain-driven design has a concept around this, which is what they call a bounded context, like that. So if you're in the chemistry business, that word means unionize. If you're in the business, the domain of business, that means unionize. Let's think of another example. How about spam? What does spam mean? Well, if you're a supermarket, spam means canned meat, and if you're an email admin, it means junk mail, right? Well, those are kind of really obvious. Okay, that's kind of easy targets. But what about product? What does a product mean? So, to a salesperson, a product is anything you can sell. Now, if you're in a warehouse, if you're managing warehouses, products tend to be physical things that you actually have inventory of. And I've worked in a business where they have a warehouse thing and they have a sales team, and there's kind of confusion about what they're talking about sometimes because they both use the same word, but they're talking about different things. So in domain-driven design, the idea is you keep both the words because you're talking to different people, but you wrap them in this little boundary and make sure they can't cross the boundaries. So the words only have meaning within a boundary. Here's another good example, customer. And you probably run into this too. To marketing people, customer is anything with a pulse, anything with an email address is a customer. And to the finance people, customer means somebody has an account with us, somebody who's given us money, something. So quite different meanings. It may not be obvious at first glance. They're talking about different things. So another thing in the world of domain-driven design is what they call ubiquitous language. And if you're working in a particular domain, say chemistry here, you have some jargon that you use. If you're working in trading business, you have jargon, and each business has their own jargon. One of the things as developers is we come in and we say, we're not going to call it a polymer, we're going to call it a linked list of molecules, because that's how it's represented in the code. And then immediately you start getting disconnect between the chemists say, what's a linked list of molecules? And we say, well, that's what it is. And they say, well, isn't that a polymer? And, you get disconnect. So the idea of domain-driven design is you use the same words the domain is using. If you have a polymer, call it a polymer. Don't call it a linked list of molecules. Same kind of thing. Every business has their own ubiquitous language, and it's often the same words will crop up. So in a sales system, we might have product and tracking, like tracking meaning Google Analytics. But in a warehouse, a product is a different thing, and tracking is a different thing. So it's very important to be aware of these distinctions. So let's look at an example of a very simple design. So this is a design for a card game, and there's various types here. So the first thing I want to point out is this is a card game, and that's the bounded context. So if I was talking about suits in a clothes business, I'd be talking about something else. And if I was in the Navy and I talked about a deck, I'd be talking about something else. So these words are relevant to the card game context. And those words then basically form the ubiquitous language of the system, of the design. So I'll quickly go, for people who are not familiar with F#, I'll just quickly run through how this works. The vertical bar means a choice, so a suit is a club or a diamond or a spade or a heart. The star is the multiplication, literally, so it's a suit, a pair of a suit and a rank. That's what a card is. The list type is built into F#, which is very nice, especially for this kind of thing. And finally, the ones with arrows are functions. So that means the input is the deck, and the output is a deck, a pair of a deck and a card. So when you deal, you start off with a deck, and after you've dealt, you have a new deck, which is missing a card now, and a new card on the table. And when you pick up a card, you start off with a card on the table and your own hand, and after you've done the pickup, the card on the table's gone, and you have a new hand, a different hand. So there's an example of that domain. So let me point out some things about this. Do you think this is a reasonable amount of code to write for this domain? And I think so, yes. I think we've got 9 different types here on one page. I think that's pretty impressive. Do you think a non-programmer could understand this? And I think so. I think let's say I'd made a mistake, and let's say I've forgotten to have hearts as a suit, okay? And somebody who was a poker player or somebody could show, it's like, you forgot to put hearts in. They could figure that out from this code. I wouldn't have to show them, reams and reams of classes for them to tell me I made a mistake. A couple of other things about this is design is completely persistence ignorant. Persistence ignorance means you don't have anything to do with databases, okay? You may need to store a deck of cards in a database somewhere, but this design has got nothing to do with that. It's all about the design, the domain. When you have real cards, you don't worry about storing them in a database. So database-driven design tends to say, okay, so we need to have a table to store the cards, and then we need a foreign key that points the card to a deck, and so there's no foreign keys in here. There's nothing about databases, nothing about entity relationships and all that stuff. It's pure domain design. The other interesting thing about this is the design is the code and the code is the design. Now, one of the holy grails of agile development is the code is the design. You don't have comments. You don't have documentation because the documentation goes out of date. The comments go out of date. The best documentation for the code is the code itself because the code is the definitive thing. And what's great is this is the definitive thing. This is code. This is not pseudocode. This is code. You can compile this code. So to me, this totally meets the kind of ideal of an agile documentation because it can't possibly be wrong because it won't compile. And if you change this design, the code won't compile, and they both always have to be up to date. So you don't need any UML diagrams. Okay, we don't need no stinking UML diagrams. This code is clean enough. I think this code is clean enough to use instead of a UML diagram. And a UML diagram is just another thing that gets out of date. So, moving on to the F# type system. So the F# type system is algebraic types, and for people who are not familiar with algebraic types, it's completely different from the kinds of types you're used to if you're used to C# or Java or Python or mainstream languages. So F#, Haskell, OCaml, they all use algebraic type systems. Algebraic is another mathy word, so I'm going to call it composable types instead, because that actually represents how useful they are. It's much more useful to call them composable, I think. And what I mean by composable is it's like Lego. Okay, just like you can glue Lego together to make a bigger piece of Lego, you can glue types together to make bigger types. So, how do you make new types in an algebraic type system? Well, you have some primitive types like integers and strings and booleans and so on. And then you make new types by gluing them together in different ways. And there's two ways you can glue them together. The first way is by multiplying them together, and the second way is by adding them together. Okay? Now, if you're not used to this, you might think this is absolutely crazy. How can you multiply types together? That doesn't make any sense at all. And how can you add types together? That doesn't make any sense. So what are people talking about when they're talking about adding and multiplying types? Okay? So I'll just take a couple of minutes to explain that. So here's a function, which is a black box. It's going to use the typical metaphor for a function, and it's got an input and an output. And I'm going to have a function called add1, say. So the input for this function is any integer, and the output of this function is any integer. And so we write it as integer arrow integer. Okay? That tells me that function takes an integer and outputs an integer. So that's straightforward enough. Now, let's say that we have something that adds pairs of numbers. Okay, so the input is any pair of integers, and the output is the sum of those two integers. So the output's easy enough. The output's an int. But what type is the input? All right, how can we represent that pair type in our model? Okay. Now, in an object-oriented system, you define a class for it, but I'm not defining a class. I'm going to compose it from smaller types. So let's think about what a pair means. So when you have a pair, what a pair really means is you take one from the first pile. So you have a pair of numbers. The first thing is an integer. The second thing is an integer. So you have one from the first pile and one from the second pile. And if you think about it, let's say there are 4 things in the first pile and 4 things in the second pile. How many combinations are there? How many different pairs could you possibly have? Well, you could possibly have 16, right? If there were 10 things in the first pile and 10 things in the second pile, how many possible combinations? There was 100, right? So it's that one times that one, all right? So that's why you call it multiplying the types, because it's that pile times that other pile. So let's look at Booleans. Let's say Booleans, the pile, one from the first pile, one from the second pile. There's 4 possible combinations. That's the same as multiplication. So when you write these types down, a pair of ints is written int star int, as if you're multiplying the types. All right? I think that's quite nice. It may look a bit strange at first, but it actually makes a lot of sense when you understand what's going on. Similarly, a pair of booleans is written bool star bool. All right? So that's kind of theoretical. It sounds nice and stuff, but how is that actually useful in practice? So let's look at a really more practical version of this. So let's say you have people's birthdays. So you have a bunch of people, and each person is associated with a date, and that's their birthday. How can you model that using this technique? Well, you have a list of people, right? And you have a set of dates, and the universe of every possible birthday is every possible person combined with every possible date. Now, only a very, very small subset of those are real people's birthdays, but in theory, all of those things are possible birthdays. So it's exactly the same thing. You multiply them together. So if you're going to write it in F#, you'd say type birthday is person times date. And that is the kind of code you'd actually see in an F# application that was, these are not low-level things like integers and booleans. These are real, high-level types that have been multiplied together to create a new high-level type. All right. So that's multiplication. And record types are actually the same thing. They're just, if you take a record type like a first name and a last name, that's a string times a string, because every possible first name and every possible last name, but they've got labels. So I'm just going to label the first one first name and label the next one last name. So a record type is also a product type. Choice types are completely different. So let's think about choices. So let's say we have a function that tells me whether I have a fever or not. And the input is a temperature, and the output is a Boolean. So if it's more than 101 Fahrenheit or 38 something centigrade, I don't know what it is, then you have a fever. Is that right? 38? Yeah. So, but here's the problem. It could be Fahrenheit or centigrade, right? It could be both. I want to be able to see, it's a really nice function. It's a generic function that works at any kind of temperature. I could also put Kelvin in there if I was going to be really nerdy. So the question is, how do we model that? All right, what type is that thing? So let's think about it in the same way. we have a list of all the possible temperatures Fahrenheit, and we have a list of all the possible temperatures Celsius or centigrade. Now, it's not every possible combination. It's one from that pile or one from the other pile. Okay, I can have a Fahrenheit one or I can have a Celsius one, but I can't have both. So if there are 4 in the first pile and 4 in the second pile, the total number of combinations is 8. All right, it's only 8 choices I can have. If there are 10 in the first pile and 10 in the second pile, that's 20 choices altogether. All right, so we use addition. So this is a sum type. I'm adding Fahrenheit to Celsius. So how do we represent that? Well, we're going to have to tag them. Because these are both integers, we need to distinguish them somehow. So typically we tag them. We're going to tag those ones with F. We're going to tag those ones with C. And then we write the type like this. Type temperature is either a Fahrenheit of int or it's a Celsius of float, say. And now we have a temperature type that actually can store one or the other, can store either kind of temperature. So again, you say, well, that sounds a little bit arbitrary. Let's look at a real example. So here's an example, actually, I do have used myself, a payment method if you're doing an e-commerce site, say. And for this, or maybe not e-commerce because I've got cash here, but a payment method, you can say, I take cash, or I take a check, or I take a credit card. Now, those are the 3 payment methods I take. The best way to model that is a cash or check or card. That's a very natural way of modeling that particular system. Notice that with the cash, I don't actually need any extra information. For the check, I have a check number. And for a credit card, I have 2 pieces extra data, the card type and the card number. So not only can I model the fact that there's 3 different payment methods, but I can attach data to each individual one. So let's see how I would actually use that in practice. Let's say I wanted to print out the payment method. You use the match functionality in F#, which is the pattern matching functionality is really powerful. Highly recommend that you understand how that works. So in this case, if I match it with cash, I can say paid in cash. If I match it with check, I bind the check number variable to that at the same time that value gets assigned. If I match it with a card, I've got those 2 things, and I can print those out at the same time. So what's really nice is you match and you can assign to those values at exactly the same time. Just quickly, for people who are used to OO, you'd say, well, a lot of people say, well, this sounds a bit like inheritance. How is this different from inheritance? So let me just quickly go through how you might do this in an OO design. So in an OO design, I'd probably have an interface, payment method, and I'd have 3 different subclasses, each implementing payment method. And each of the subclasses would have their own data inside them. So the first question is, what goes in that payment method? There's not a lot of behavior which they have in common, maybe printing or something, but I don't really know what the behavior is. And so probably what I'm going to end up doing is having switch statements where I cast things in turn. If I can cast it to a cache type, then it's this. If I can cast it to a, that's kind of horrible. I can use double dispatch. I can use visitor pattern. There's various OO techniques to handle that annoyance. But when you have different subclasses and they have different behaviors, it's quite tricky to model in OO. The other nice thing about the functional design is that the data that I need is really obvious. And here, it's not obvious at all. Because I've got 4 lines of code in the F# version. And here, if I was doing this in C#, I'd have probably 4 different files. And they might not even be in the same folder. And so if I want to see what's the difference between cache and check, I'd have to look in at least 2 different files to understand what the difference is, which I think is quite annoying. It's quite nice to see all the stuff right there and very explicit. Finally, that payment method is what you call the closed set of options. Like, I can't add another one easily. So if I want to add another type of payment, like I want to take PayPal or something, I have to add it explicitly. And then all my code breaks. Everywhere that I've got payment methods is going to now have to handle PayPal, which I think is a good thing, because if I'm adding a new payment method, I want to know all my code which handles payment, because I want it to handle PayPal now. So to me, breaking my code when I add a new payment method is exactly what I want to have happen. In an OO thing, it's open, which means I can add subclasses without anyone knowing. So I could add an evil payment method, and as long as it meets the interface, I could use it anywhere I like, and nobody would know. So, there's a debate. There's this thing called the expression problem, which is which one, they have pros and cons, but I think for business modeling, I personally like the explicitness of a choice type, a discriminated union like this. I think it's a lot nicer than OO. Okay. Hmm? What? The previous one, whoops. That one? I have to basically go and find all these switch statements and add a new one, because the compiler will say, unlike with C#, the compiler will say, I forgot to handle a case. If I add a new case, it'll actually be a compiler error. Well, it's actually technically a warning, but I mean, to me, it's a serious warning. You can do the same thing in a. There's no really equivalent. In a switch case, you have a default, but if I add a new subclass and I forget to handle it, it just goes into the default, and I might not ever know that I forgot to handle it. There is a way of doing defaults in F#, which is use an underscore. So if you see someone do, like, if I had vertical underscore, yeah. So that means that that's the default, and it'll match anything. Then you won't get the warning. It's considered a bit of it depends on, if you really, really want to make sure that I would only do that in situations where I'm forced to do it. But if in this situation, when I have a limited number of types like this, it's a good practice to always explicitly match every single case. Yeah, I mean, in this particular case, I've got 3. Now things like integers. If I'm matching integers, I don't want to have 32,000 matches. So you have to use an underscore there to tell the compiler you're happy. But in general, this kind of thing is better to have explicit matches all the time. Okay, where are we? Right. So what are types for in F#? So if you're used to C#, types are really an annotation for type checking. So we say, this is an integer. And because it's an integer, I can't add it to a string. Okay, so that's what we think of what types are for. But I think you can also see that types in F# are a domain modeling tool. You can actually use them to represent a design. And what's great about F# is you get both for the price of one. So you model the types using your domain as a domain modeling tool, but then the compiler does type checking for you. So you can actually think of the type system as compile time unit tests. So if you can get your code, if you can represent your logic in the type system, you don't need to write a unit test. I mean, for example, if in a static type, I don't need to write a unit test to say that I can't add a string to an int. The compiler will say I'm not allowed to do it. I don't need to have a test for that. In Python, I might need to have a test, but in C# I don't. Now imagine taking that same kind of power and making it even more so that you can all the other business rules are actually encoded in the type system. And that's what I'm going to talk about next. So, type all the things. This is why people like static type systems, because you can get a lot of power out of them. All right, so designing with types. What can we do with this type system now that we've seen it? Let's take it out for a spin, see what we can go. So let's go back to one of our original examples, a personal name, and let's see if we can fix it up a bit. So let's start off by talking about required versus optional. So here, the middle initial is optional, and the first and last name are required. So how can we model that? So a lot of people say let's use a null, all right, to represent a missing value. And I want to say nulls are evil. Nulls are terrible things, and I'll explain why. You don't ever say set phasers to null. It's not a logical thing. Nulls are not a logical option. Spock would not approve. So why are nulls so bad? Well, let's say we have this function called length, and it takes a string and it returns an int. So it's the length of the string. Okay, very easy. So I go along and I'm saying, A, how long are you? Well, I'm 1 long. And I talk to B and I talk to C, and I talk to null and I say, how long are you? And it gives an evil cackle and it crashes my program with a null reference exception because it's not a string. It doesn't have a length. Why is it pretending to be a string? It says, oh look, I'm pretending to be a string, but I'm not a string. So it really shouldn't belong in the pile of strings. Null should not be there. So null is not a string. And I call null the Salmon of static typing because it's pretending to be something that it's not. It's misleading you. It's a turncoat. It's a traitor, you know. So don't use nulls as values. Now, in this case, unfortunately, because of .NET compatibilities, string is actually one of the examples where you can actually put a null in. But for most of the types that you define yourself, null is not a valid value for a type. So don't use nulls. So if you don't use nulls, what can you do instead to represent missing values? Well, let's go back to how we talked about our choice types, our sum types. So we have a list of things. It could be a string, or it could be not a string. It could be missing. Okay, that sounds exactly like what we had with our temperature, with our Fahrenheit and our Celsius. It's one thing, or it's another thing. So it's a perfect setup. We have a pile of one thing, a pile of another thing, and we're going to add them together. All right? So I'm going to use a tag, how we tag each set with a different label. I'm going to tag those with some string, because there's something there. And I'm going to tag that one with nothing, to tell me there's nothing there. And that, when I put them together, I get this type, which I'm going to call optional string. Okay? And it's got some string, and it's a string, or it's got nothing. So can you see how we can build that optional type? It's very simple, I think. Okay, so we're going along and say, oh, this is fantastic. What a great type. This is really useful because I've now got a nice type-safe way of marking things which have missing values. And then you go along and you say, oh, I've got optional string, and then I've got an optional int, and I've got an optional bool. And it's like, oh, I think there's a pattern here. I think I've got a lot of duplicate code, right? How can we make it a bit more generic? Well, the answer is to have a generic type, okay? So that T is a generic type. That's F#'s way of doing it. It's always got a tick in front of it. So luckily, this type is built into F#. You don't have to define it yourself. And not only is it built in, there's a nice little library with some functions on it. So very, very useful. Every time you have missing values, use the option type. So let's look at how we'd use it in this example here. So instead of the middle initial being a string, we'd turn the middle initial into an option of a string. Okay, so that tells me at a glance it's optional. And in F#, one of the nice things you can do is you can actually swap them around. You can just say string option. And I think that's a really nice way of designing, because I can actually show that to somebody, and it's like it's a string option, or it's a string. And it's very, very clear, very easy to understand. All right, what else can we do with these types? So there's something called I call them single choice types, single case types. It's a choice type or a sum type with exactly one choice, with one case in it, like this. I've got something is a choice A of A. There's no choice B, there's no choice C. There's just one choice. And you think, well, why would I ever want just one choice? What possible purpose does that solve? So let me give you some examples. Here we have an email type, email of string. And here we have a customer ID of string. Why would I bother to create types like that? The answer is that they are distinct types. Email address is not a string. Email address has certain validation rules. Maybe it can't be more than 250 characters, and there's certain rules about it. I mean, email addresses are not strings. Okay. A customer ID is not an int. You might represent it as an int in the database, but it's not an int. You can't add 5 to a customer ID, right? It doesn't have, you can't have a negative customer ID. You can't multiply. It's not an integer. You might, as it is, the representation behind the scenes might be an integer, but it's not an integer. It's its own thing. A customer ID is a domain concept in its own right. So single choice types can help to keep them distinct. So here we have two single choice types, an email address and a phone number. And they're both represented by strings behind the scenes, but they're different types. So I can't ever accidentally mix a phone number in where I was expecting an email address, and vice versa. Here's another good one, a customer ID and an order ID. Again, they might be represented by integers behind the scenes, but they're different things. In fact, this is a common cause of bugs, is when you accidentally mix them up. It also acts as a form of documentation. If I have a method or a function that says retrieve from the database, this custom ID, if I have a type called custom ID, it's really obvious that I'm expecting a custom ID. I'm not expecting an order ID. It's actually self-documenting when I do that. The primitive obsession, I don't know if you've heard of that phrase, that's the idea that in a lot of languages people can't be bothered to create types for things. And I agree, it's quite painful in C# to create hundreds and hundreds of these little types. So you end up having everything be a string, because you just can't be bothered to wrap it in a type. And you can't be bothered to wrap the ints in type. So you have integers floating around, you have strings floating around. So that's called primitive obsession. And I'm guilty of that myself when I write C# code, because I literally can't be bothered to write all these types. But in F#, it's a one-liner. There's no excuse not to write a type. So it's actually easier than not to write these one-line types. Okay, so let's have a quick look at the email address type. So I'm going to create a constructor for the email. I'm going to use this as an example of how you'd use this in practice. So there's a constructor. You pass in a string, and you're going to compare it with the regex. In this case, it's just going to have an @ sign in it. It's a pretty crude validation, but there you go. Now, if it matches the regex, then I'm going to return an email address. And if it doesn't match the regex, what am I going to do? Well, I can't return the email address because it doesn't match. And I can't return, what am I going to do? I'm going to return a null. I can't return null. You want me to throw an exception? That's a bit harsh when I'm just trying to create an email address. Well, it turns out we've already seen the answer. We can use these optional types. So we replace that with a sum if it's a valid email and a none if it's not an email. And what's really nice about this is it makes it very, very clear. The constructor tells you what's going on. So originally the constructor might look like something like this. I pass in a string and I get back an email address. But when I put the sum and none on, it tells me very clearly that I might get back. I get an email address option. I might get back an email address or I might not, depending on whether the string that I passed in was valid or not. And what's great about this approach is that the client who calls this code has to deal with both cases. I can't just put my fingers in the ears and pretend that everything's fine, or just have an exception that I ignore. I have to deal with the fact that it might not be an email address, which is good, because that's exactly the cause of a lot of bugs, is you forget to validate things, So once I've got an email address, I don't have to validate it anymore. I only have to validate it once. So that's also nice, because I don't know how often you fall into this trap, but sometimes I validate things over and over because I'm not sure that the previous person actually validated it properly. But the nice thing about this is once it's an email address, I know it's valid. I don't ever have to validate it again. So I have a lot of confidence that if my UI layer has turned it into an email address, my database backend doesn't need to validate it before saving because it's guaranteed to be an email address. The only place where you have to do the check is when you create it, and that's where you need some code to say it's not valid, typically at the UI layer or somewhere. Okay. Let's use this for other things. Here's another common one I like to use. String 50. So one of the things that really annoys me is when I have a string and it goes all the way through the ULI and it comes to the database and it's like, oh, by the way, the database only has 50 characters in it. And it's like, I've got a 200-character string. What am I supposed to do now? Am I supposed to crash or throw an exception? I mean, it's like too late. I don't really want to have the database layer even have to think about that. I really want the UI layer. If it's not valid, the UI layer should give an error message straight away. But the database layer shouldn't have to care. It doesn't know what to do. It has no knowledge of what's going on. Throwing an exception, I mean, really, it's just a tough problem. Throwing an exception is terrible. Returning a bad insert or something, it's just, So it's really nice to have these things like a string 50. And once you've created one of these things, you can pass it into the database layer and you guarantee the database is going to be able to handle it okay. So here is the code for that. If it's less than 50 characters, it's good. Return some. If it's not less than 50 characters, return none. And you can see from the signature of the constructor, it takes a string and it returns an optional string 50 because it might not be a string 50. It might be too long. And again, when you create this thing, you're going to have to handle both cases. But then once you've created it, you can be guaranteed that it's never going to be more than 50. Can't possibly be wrong. Here's a good one. Let's say this is a shopping cart in an e-commerce system. What is wrong with this picture? Okay. What's wrong is I've got 999,000 things in my cart, okay, in my basket. That should never happen. That's just a bug waiting to happen. All right. So how could that even happen? It's because the person who wrote this code didn't have any validation on the integers that they could use behind the scenes. They're probably using an int, right? And I mean, you can probably see things on, funny things where it rolls over to 32k and then it rolls back down to minus 32k or something. I mean, just because people are using ints, an order quantity is not an int. All right? What you need to do is you need to create a type called order line quantity, okay? And it has certain properties. And it's a new type just for this domain. Now, this is the kind of thing where most people won't be bothered to create a new type. How many people ever created a new type just for an order line quantity? Very, very few, I'm willing to bet, because it's a lot of work, Now, in F# it's a one-liner, but in C# or Java, it's kind of annoying. See, it's like, well, I can't be bothered. I'm in a hurry, But when you have that, it's really useful, because let's look at our creation code here. I'm going to say the quantity has to be greater than 0 and less than 99. And if that's true, it's a good value, and if it's not true, it's a bad value. What's interesting here is I'm checking the quantity 0 is not a valid quantity. So there's a classic bug. You're not allowed to have an order line with 0 quantity in it. By doing this, I've immediately eliminated some sort of bug that I don't even know I've got yet. Chances are, if I look in shopping cart code from other systems, they're always checking, can you go below 0? Can you have negative quantities and stuff? By doing this, I eliminate a whole class of bug right up front. And again, it's very clear that it returns an optional type. So let's look at the original code from the first slide. We've got a first name, last name, email address. So let's see what we can do to make it nicer. So the first thing we can do is turn it into an option. We saw how to do that. Second thing we can do is put lengths on everything. And we have a special type for email address. It's not just a string anymore. It's a proper validated email address. Notice it's not optional at this point. By the time it gets here, I guarantee it's a real email address. So the UI, before it's created this structure, has had to have handled the case where the email was not valid. It's also had to handle the case where the strings were longer than 50. So in order to even create this structure, I've already done a lot of validation. So there you go. I see what you did there. It's kind of cool. I've gone from one thing to this thing. I think that's really powerful. And I think that solves a lot of bugs already. So there's two other things that I talked about on the first slide that I haven't talked about yet. So the other thing I talked about was that the unit of atomicity in terms of transactional updates. I said you want to split them up into two pieces. Well, in F# that's really easy. I can create 3 types on one page. Trivial. In C# it's like I might not want to split them up because now I've got 3 whole files to manage. In F#, it's 10 lines of code. How hard is it? So it's really easy to do the right thing in F# because the types are so easy. This last thing, is the email verified? Okay, that's worth going into in a bit more detail. So there are some rules around this. If the email is changed, then the verify flag has to be set to false. And the verify flag can only be set by a special verification service. Okay, I don't want anyone to be able to set it because that's a security hole. Well, maybe not a security hole, but it's not right. The only way you should be able to set that flag is if you're a special service that has permission to set that flag. All right. So how can you represent those business rules in that system? Probably there's code for this business rules floating around, but that's no good because just because there's code doing it doesn't mean I can't just bypass that code and just set that flag, without knowing what I'm doing. So can we encode that in types? And the answer is yes, you can, of course. That's why I'm here. So what we're going to do is we're going to create a verified email. So we're going to wrap a normal email in a verified email. We're going to create yet another type that wraps another type. Okay? And this is a quote I like. There's no problem that can't be solved by wrapping it in another type. All right? And you end up with types wrapping types wrapping types. But, it's easy enough. It's one line of code. It's not that hard. So now we have this verified email. What we can do is hide the constructor and make sure that only one person can actually create these things. And here is our verification service. And it takes an email. It takes a normal email address, and it takes some sort of hash that the user has clicked on to verify their email. And if the hash matches the email, then you get an email option. okay, a verified email option, because the hash might not match. So this service checks them up, and if everything's good, you get a verified email. Okay. So what we do then is we rewrite our email contact information as two choices. Okay, the Boolean flag is now gone. We have the first choice is an unverified email address, and the second choice is a verified email address. But the verified email address is this wrap type that I can't create. So if I come along and I want to set an email address, I can set it to be an unverified email address. I sort of have permission to do that. I don't need permission. I can just say, oh, yeah, this is an unverified email address, no problem. But I can't make it to be a verified email address, because the only person who can create that is a verification service. So by doing this, I've made it type safe, I've made it secure, and I've encoded the business rules into the actual object itself. Plus, I've actually made it clearer, because originally there was a Boolean. It's like, well, what does this Boolean do? This I can actually show to somebody and say, look, oh, it's verified or it's unverified. That's like, yeah, I understand what that means. So we've got all the ingredients now to go back and look at the first thing. We've got the email address, the verified email, the email contact info, the personal name, and the contact. So we now have 5 types where before we had 1 type. All right. Now these 5 types are not taking up that much. They're taking a bit more space, but they're still quite compact. But what's really cool is we're actually building a ubiquitous language. It's not just creating types for the sake of it. As we do this, we're actually discovering things about the domain. We're saying, oh, look, we have such a concept. We have a concept called a verified email, right? We have a concept called a personal name. So these types actually represent real things that the business cares about. And we might start having business rules. Once we have these things, we might start having business rules, like verified emails can only be used for this thing. If we want to do something, we have to use a verified email. That might be a business rule. And there you go. You've got the type all ready to go when you need to do that. By the way, this is compilable code, as always. This is not a UML diagram. This is not a comment. This is not an architecture document. This is code, right? This is code and documentation in one thing. All right, so we're doing fine, and then suddenly the business changes, as businesses tend to do, and we add an address. So now our contacts are not just emails, they have addresses as well. Okay, that's fine, not a problem. But now the business comes along and say, actually, you know what? We have this new business rule. A contact has to have an email or a postal address. We have to have some way of contacting them. So I look at this and I say, well, does that type meet the rules as it stands? And the answer is no, it doesn't. Because as it stands, both the email and the address are absolutely required, right? There's nothing about being optional, they're required. Well, that's not good. I don't have to have both of them. So I say, okay, well, that's easy. I'll make them both optional. But that doesn't meet the requirements either, because they could both be missing now. All right? And they've got to have at least one. You can't have neither. And this is the kind of thing you'll see a lot where people check that, oh, they both know, and there's little validation codes. Like, is there a way to encode that in the type system so that you can't possibly mess it up? So this doesn't meet the requirements. How can we write some code that meets the requirements in a way that I literally cannot get it wrong? So here's a quote: make illegal states unrepresentable. This is by Jan Minsky, who's an OCaml guy, but F# very, very similar. And the trick here is you actually make it so you literally cannot write down something that can't happen. Okay? If you can't write it down, you can't have a bug. I mean, you can write it down, but it won't compile. You literally cannot compile code that doesn't work. So let's look at this thing. What does this mean? A contact must have an email or a postal address. That means they have an email address only, or they have a postal address only, or they have an email address and a postal address. That's it. There are only 3 possibilities, right? Not 4. All right? So how can we encode 3 possibilities using our type system? Well, we have an email-only choice, and we have an address-only choice, and we have an email and address choice. So we've encoded exactly that business rule into our type system. There is no 4th choice. There is no, email missing and address missing choice. So you literally cannot have both of them missing because it's not one of those choices. And now before we had a separate email address and postal address, and now we have a generic contact info. So only 3 possibilities. And the requirements are encoded in the type. So let's review that. We started off over here with an email address as separate things. And then what we did is we merged them into a single type, which is contact information. And that contact information is a choice type, one of those 3 situations. Okay? So, F# is awesome. Okay? Static types are almost as awesome. So nothing's quite as awesome as that. I mean, this is the epitome of awesomeness. But static types are pretty awesome because who would have thought you can actually encode business rules in your type system so you literally cannot make a mistake. I mean, I didn't need to unit test all that stuff up front. You know, when I said you can't have a customer having more than... I don't have to write unit tests saying for that business rule is right in the type system. And it's documenting. If someone comes and looks at that, and they say, well, what's the business rule for contact information? And I say, well, they can have an email, or they can have address, or they have to have both. It's right in the code. Self-documenting. All right. Now, let's look at a change. The business changes its mind a bit. And they say, you know what? We don't really need to be that strict. What we really want is that a contact, we just have at least one way of contacting a contact. Okay? We don't really care how we contact them. We just need some way of contacting them. So it's a subtly different business rule. And we can actually have a subtly different design to represent that. So in this case, we're going to design a contact info. So this is some way of contacting somebody. You can be contacted by email, or you can be contacted by post. Okay, so there's 2 different ways to contact you. And then our contact type looks like this. So our contact says there's a primary way of contacting you, which is a contact info, and it's required. And there's a secondary way of contacting you, which is also contact info, but it's optional. So this is a subtly different thing because the primary and the secondary contact could both be email, they could both be post. So it's not exactly the same. But probably this is actually what the business really wants. They just probably want ways of contacting people. How are we doing for time? Anyone? Huh? Another 10 minutes? Okay. So I'll just finish up with states and transitions. This is a very common scenario in blobber development. I run into all the time. I think it's just worth talking about quickly. So when I talk about states and transitions, I mean a very simple state machine. You have a state and another state, and you have some sort of way of transitioning from one state to another. Now, if you're familiar with state machines, you're probably thinking compilers, parsers, complicated stuff, you know. I'm talking about really, really simple states. I'm talking about 1 or 2 states, and I'm talking about 1 or 2 transitions. So I'm not talking about something where you need to build a parser generator. You know. I'll show you what I mean. We've already seen one, which is our email address. Okay? We have an unverified email address, and we have a verified email address, and you can verify an unverified email address. That's it. You can't go backwards. Once it's verified, it stays verified. So that's a state machine right there. And these are 2 different states. All right? So there's a real example of a state machine we've already seen. And this pops up all the time. You'll find that almost always in business rules, there's these things. If the customer is this kind of customer, do this. If this kind of customer, do this, and this, they can change from being a prospect to a customer to being a valued customer to being an inactive customer. Lots and lots of states. Typically, there's business rules which are specific to each state. So in this particular case, you might have a rule that says you can't send a verification email to somebody you've already verified. All right? So it means that the business rule applies, to the unverified email address. And similarly, you say, well, you can't send a password reset to somebody who has an unverified email. So the different business rules for each state. That's a very, very common situation. Here's another one. You're doing shipments, deliveries. It starts off being undelivered. It goes out to delivery. It gets signed for it's delivered. If the address isn't found, it gets put back in the warehouse again. But there's all sorts of business rules. You can't put a package on a truck or a lorry if it's already out for delivery. You can't sign for a package that's already delivered. These are the kinds of things that are so bug prone. I mean, state machines are great because you're always dealing with errors if you don't have it like this. So I'm going to talk about one of my favorites, which is a shopping cart or a shopping trolley, shopping basket. You have an empty cart, you have an active cart with stuff in it, and then you pay for it. When you pay for a cart, it's paid for and it's done. You can't add things to it anymore. It's immutable. You can remove things from a cart, and if you remove too many things, you go back to being an empty cart. But you can't remove something from an empty cart. So there's a bug eliminated right there. So, rule, you can't remove something from an empty cart, you can't change a paid cart, you can't pay for a cart twice. These are classic business rules. If you design it as a state system like this, you literally get these rules for free. And you don't have to worry about bugs. So, how do we actually design a system to handle this kind of thing? So, first of all, what data do we need to store for each state? So, typically, there's different data for each state that you need to store. So, for the empty cart, there's no data. You just have, it's empty. There's nothing in it. For an active cart, you might have a list of unpaid items. For a paid cart, you'd have a list of paid items plus the payment that went along with it. Let's see. Right, so let's put them together. So we have our active cart, we have our paid cart. So the shopping cart is going to consist of 3 different cases. The empty cart case, the active cart case, and the paid cart case. And for those 2 cases, we store the data associated with that state. All right? So we define the data that we store, and then we define a case for each possible state. So once you've done that, you can now define an API. Okay? So there we go. Let's define our API. So we start with an empty cart. We initialize it by adding something, and we get a new shopping cart. We add something to an active cart, and we get a new shopping cart. And we remove something from an active cart, and we get a new shopping cart. And we pay for an active cart, and we get a new shopping cart. Notice that I'm returning a shopping cart. I'm returning something that can be any one of those states. I'm not saying it returns an active cart, and I'm not saying it returns an empty cart. I'm saying it returns a shopping cart. So you do not know which one of those states it's in, and that's deliberate, because you don't know, really. It could be either, depending on the situation. So that's a very common pattern in the API, is you have a very specific thing that you deal with on one side, but what comes out the other side is any one of those states. So when let's look at the server code quickly. So to initialize a cart, we just put some stuff in a structure, very easy. To add something, we just prepend the item to the existing items, and so on and so forth. So the code is very straightforward. But let's look at the client-side code. So let's say I'm adding something to a cart. So the cart is 3 different states, so I need to handle each possible case. So if the cart's an empty cart, I need to initialize it. Fair enough. If the cart's an active cart, I need to add it to an active. But if it's a paid cart, what do I do? There's actually no way I can write code that messes it up. The API is not there for me to write. I cannot pay for a cart twice. I cannot remove something from a paid cart. I can't add something from it. It's just literally the API is not available to me. So this is guaranteed you have bug-free code. The client cannot possibly mess your code up. So that's really, really valuable if you're writing an API. There are ways to do this in C# and Java. Basically, you have a function, a method with a lambda for each possible case. If you go to my website, I explain how it's done. But it's really a bit of a pain, and in F# it's so much easier. To remove an item, same kind of thing. We remove items from the list, and then if the list is empty, it's an empty cart, and if the list is not empty, there's that underscore again. We turn it into an active cart. All right. So let's look at the client code to remove an item. So if the cart is empty, what can I do? I can't do anything. I can't remove an item from the cart. So the client is pretty much forced to show a message saying, I'm sorry, I can't remove an item. In fact, what the client really should have done is disable the button to remove an item from the cart. But if the client was stupid enough to not have done that, they're going to have to show an error message or something. But no matter how stupid the client is, they can't mess up your code. So I'm assuming that you hate the people who are writing the client code. I mean, the Java. Let's say you've got a web service and you've got an Ajax client or something. It's like, I don't trust the people writing the JavaScript. So same thing with the paid carts. I literally cannot mess it up. There's nothing for me to call, so I can't even call the wrong kind of function. So why design with state transitions? Because it's a good way of, each state can have different data, like we saw with the paid cart and the unpaid cart. All the states are explicitly documented. This is what I like most of all, I think, because when you're writing shopping cart stuff, you very rarely, not normally would you have an empty cart as a special type. I mean, the amount of times I've seen that in real life code is never, basically. But if you're doing it in a functional way, it's really obvious. I mean, it's like it comes out naturally. And all the transitions are explicitly documented. I mean, every possible transition you have to think about. Well, can I go from an empty cart to a paid cart? No. So that's not in the API. Can I go from a paid cart to an empty cart? No, that's not in the API. So it's very clear. The API is just a set of transitions. So it's a design tool that forces you to think. That's what I like about this approach. Just to show you that example again. Okay, so what have I talked about? Ubiquitous language, self-documenting design. I think that's fantastic. Algebraic types, products and sum types. Designing with types using options, using single case unions, using choices rather than inheritance, making illegal states unrepresentable, and then finally states and transitions. So there's a lot of stuff you can go forward with this. Services I haven't talked about, CQRS, use cases, domain events, error handling, and so on and so forth. This is really, like I said, just scratching the surface. So for any people who need to persuade their manager, the F# is really a good thing to do. It's like if you're sold, it's like, how do I tell my manager that F# we should be using F#? Well, first of all, F# is great for enterprise development because it's supported by Microsoft. So if you're a big company and you're doing enterprise development, Microsoft's got you covered. If you're doing mobile development, Xamarin's got you covered. And between the two of them, you've got F# basically everywhere. So it's a very low risk. Plus you've got F# on Linux as well. So F# is a safe choice. It's not an unsafe choice. And another classic argument your manager will say, well, there's not enough F# developers around. And all I can say is, how many people belong to this user group and how many people would love to have an F# job? So there's no shortage of F# developers either. If you do need to persuade your manager, I have a special page on my consulting site, whyf#.html, and it has all the reasons why you should use F#. So if you just go to my fpbridge.co.uk. So I love F#. If you want more on DDD, that's my DDD page. Lev Gorodinsky has a couple of really nice blog posts about DDD. Thomas has a blog post about type-first development, which is similar. And F# on Twitter if you've got any questions. If you want to contact me, that's my Twitter handle. And that's my consulting business. If you need any help with F#, some training, or not you, but if your manager wants to hire me to do some training, or consulting, or some coding, well, just let me know. I'll be happy to help. Thanks very much. Okay. Do we have time for questions? No time for questions, I'm sorry. If you want to come and grab me, I'll be around. I'll be hanging around a while, so just come and grab me if you've got any questions.